Hey guys, welcome back to another video. In today's video we are going to understand some important concept of vector database and vector index. First we will understand what is a vector, what is an embedding, the difference between these two. Then we will understand what is a vector database. Then finally we will cover what are vector indexes. These are very easy concepts, but they are very much essential when you're working with generative AI. So without any delay, let's get started. While working with embedding, the first thing that we have to understand is the difference between a vector and an embedding. A vector is a simple numeric representation of a context. Suppose if I have a sentence like I like apple, a vector representation of this sentence will look like this, where each element is a number. It can be an integer, it can be a float value, anything, but it will always be a number. And each of these numbers is called as a token. This is all about the basics of a vector. Now let's understand what is an embedding. If I take these vectors, they do not have any meaning behind them. They're just simply words converted into numbers. But if I capture the semantic meaning, the positional meaning, etc., then we will have something called as an embedding. Let's go ahead and create a very simple embedding and see how they actually look like and how is it different from a vector. There are many popular embedding models out there, the most popular one being OpenAI embedding, which uses GPT 3.5 Turbo, but it's a paid one. So for today's demo, we are going to use Hugging Face Sentence Transformer, and this is the name of the model that we will be using, all mini LM v6. This is an embedding model available directly from Hugging Face. It doesn't require much computation power as well because it's very lightweight model, and the best part is it's absolutely free. So let's go ahead and implement this. Okay, here you can see I'm importing my sentence transformer, and I'm just storing a couple of sentences inside of this list called as sentences. And this is where I'm creating an object of my sentence transformer, and I'm passing the name of my model here. And now I've got a few lines. Actually, we don't need this one. Okay, I've got a few lines here. Biryani is a flavorful rice dish, so and so. Samosas are crispy pastry, so and so. Butter chicken. So I'm taking these lines and I'm going to convert them into embeddings. So I'll say model dot encode of lines. So this will give out embeddings. Let's see how they look like. This is a list of 3 different embeddings, one embedding per line. Let's take one of these embeddings and see how they look like. Let's take the first one. Here you can see how an embedding actually looks like. It is of float 32. Let's see the shape of it. So there are 384 tokens inside of this. So this is how an embedding actually looks like. Let's see what we can do with these embeddings. Here I've got a user question. What is your favorite Indian dish? Now I'm going to convert this into an embedding, and then I'll use model.similarity, and I'll pass my previous embeddings and my question embedding. So what this does is it will calculate the similarity between all of my previously calculated embeddings with my question embedding, and it will give out all these similarities here. You can see it is 0.38, 0.45, or you can say 38%, 45%, 34% similar to these 3 embeddings. Now if I take this part and if I convert that into an embedding and then check the similarity again, here you can see it is 92% similar. So this is how we can do similarity matching inside of 2 different embeddings. Let's see how we can store and manage all these different embeddings. For that, I'm going to use something called as ChromaDB. This ChromaDB is a vector database where we can store all of our vectors. In our case, instead of vectors, we are storing our embeddings, but we will call it as a vector database, even though we are storing embeddings. So in this piece of code, you can see I'm importing my ChromaDB and I'm creating a client of my ChromaDB, and then I'm getting a collection. So collection, as the name suggests, it's a collection of different embeddings. So in this particular piece of code, you can see that it's an empty collection. So get or create, if I don't have it already, then it will create that collection. If I have it already, it will get the existing collection. And then I'm doing an upsert operation where I'm taking all of my documents and I'm passing some IDs as well. So the first document will be associated with the first ID, and then an embedding will be created automatically by ChromaDB and it will be stored inside of my Chroma client. But if I want to use a custom model like the one that we have used above, if I want to use this exact same sentence transformer, we can do that in ChromaDB. So let's go ahead and see how we can do that. Using sentence embeddings with ChromaDB. Here you can see from ChromaDB utils I'm importing embedding functions, and with embedding functions I'm just going to have sentence transformer method where I'm going to pass my model name. As you can see, it's the exact same model that we had from Hugging Face. So it's already present inside of ChromaDB utils. So I'm going to create this variable where I'm storing this entire embeddings function. So I'm calling it as sentence transformer EF. Now here I'm just taking a couple of sentences and I'm storing them inside of documents, and for each of these document I'm creating a metadata store as well and some IDs. So inside of metadata you can store as many things as you want, whichever metadata is relevant to your particular document. In my case, because I'm just passing a string value, I'm just storing the source as recipe book, source as food blog. But if you are using some kind of a document text, where if you are using OCR or some other technique, if you have passed everything from that document, then you can store the metadata like the number of pages, name of the document, when was it created, so and so. All of that can be stored inside of metadata, and also a unique ID. Now I'm just simply doing a dot zip with all these three. I'm taking the document meta and ID and I'm passing them here. And for the embeddings parameter, I'm just going to pass my function and I'm going to pass my document. I'll take the actual embedding, and this is where I will be storing that embedding. So if I have to take this whole part out, I'll put it here. Let's run this. And doc, this is a sentence. Here you can see I'm getting an array. So this is my actual embedding. I'm going to, let's see the shape of it. So this embedding of 384 tokens will be taken and it will be stored inside of this collection along with the ID metadata and the actual document itself. Let's go ahead and query them. So here you can see I'm using collection.query and I'm passing this particular question. Now automatically this will convert this into an embedding and it will search for the most relevant embeddings and it will give out two results. I'm passing n number of results as 2, so I'll get two different results. Here you can see I've got two IDs, dish1 and dish2, and if I go into documents, you can see this is a list where the first one is the most relevant and this is the second one. So in this way we can query a collection as well. Now so far we have been converting only these small simple sentences, but when you're dealing with an actual data set or even a simple PDF file, you'll have a huge corpus of text. So what we do is we take that huge corpus and then we split it into multiple parts. Let's see how we do that. Here you can see I've created something called as long text, and when I print it, it is giving me an actually long text. This is all just one long string. Now what I am going to do is, from LangChain, I've imported something called as recursive character text splitter. It's a very popular method that we will use to split our text. I'm going to give something called as chunk size, which is 200, and chunk overlap as 20. So let me show you what happens when I split the text. I'll run this. When we take a look at chunks of 0, you can see my long text has been split into a small part where the size of it is only 200. So you can see it stopped at this point, across the country dot paneer. If I go up, so it started from here, and until this point it considered everything as one chunk. Now if I reduce this size into 100, dishes like biryani, a dishes like biryani, a. So you can see that when I reduce the chunk size, the size of each sentence is also short. Now the second thing is chunk overlap. Let's print chunks of 1. You can see this ending part is present in the next chunk as well. So this is called as overlap. Let us increase this overlap value to 50. You can see there is no change in this first chunk, but in the second chunk it started taking from this point onwards. So this is chunk overlap and chunk size. Depending upon your dataset and depending upon how much information you want to retrieve, you will have to decide on the chunk size and the chunk overlap. Here you can see I've created a custom embedding class which is borrowing the LangChain basic embeddings, and inside of this I'm passing my sentence transformer. So when I pass this model name here, you'll get it inside of the sentence transformer, and we will be creating that as the actual model. And I'm creating two different methods here called embed documents and embed query. So whenever I send a document, for each of those document I'm going to take my model and then I'll encode it, which means I'll be converting them into an embedding, and I'll convert that into a list and I'll store it in one more wrapper list. Embed query is going to take a query and then it's going to do the same thing. It will convert everything into an embedding, and then I'll take the actual embedding from the list and then I'll convert that into a normal Python list. So this is my custom class. Next, creating document instances with unique identifiers. So LangChain supports a data type called as document. So this document will have three different things: the page content, metadata, and ID. So these are the three things that you have to pass for every document. So I'm going to create an object of document class. I'll pass this as the page content, metadata, and then some random ID. I'll create 10 such documents, and I'm storing all these documents inside of a list called as documents, and I'm going to create 10 unique IDs as well. Let me quickly show you how one unique identifier looks like. So every time I run this, it is going to create a unique ID. So I'll be creating 10 such unique IDs, and I'm storing them inside of a list called as UUIDs, Universal Unique Identifier. Okay, now I'm taking ChromaDB and then I'm importing Chroma from LangChain, and this is my custom embedding model, and this is where I'm passing the name of my model. So sentence transformer slash paraphrase multilingual mini LM L12 V2. So this is a different type of embedding model. It's a different variation of the same mini LM series. Now I'm creating a custom embedding of it. This is my embedding function. So I'm going to create a client of my ChromaDB, and this is the name of my collection. Again, I'm using get or create, and the name of the collection is Indian food. If it is present already, then it will get it. If not, it will create it. I'll take this collection. Now I'm defining my vector store here. So I'll say and chroma, and this is my client. This is the name of my collection, and then this is my embedding model. All of these combined together is going to be called as a vector store. Now I can add my documents and my unique IDs. So this vector store now has all of my previously created 10 documents along with IDs. Now when I perform similarity search, vector store.similarity search, I can just simply pass my query. K equal to 2 will give me top 2 matching results, and I can pass some filters as well. So wherever I want to uh, if I want to filter out all of my documents and take only those which are coming in from the source as tweet, because if you remember I've given this in the metadata. So if I want to take only the tweet source documents, then I can pass them in the filters, and the similarity search will return me those two different documents, and they'll be stored inside of results. And inside of results, I'm printing both of them, and here you can see these are the closest matching ones. So along with results, along with page content, I'll get my entire document. So IDs, embeddings, you can ignore this part, the documents, and the metadata, the distances. So everything is being given to you in the results. So that is a brief introduction to embeddings. Now let's put everything in one place. Here I'm importing OS, OpenAI, and ChromaDB, and I'm creating a client of ChromaDB. I'm creating a collection of that client, and then this is my custom embedding model. Now I'm creating a function called embed document, which will take text. It will be a string value, by the way, and it will take that string, it will send it to embed query method. So this embed query is a method present inside of my custom embedding, right? So let's go ahead and see what it is doing with that string. Too far. Okay, here we are. Custom embedding and embed query. So this will take a query which is of a string data type. It will send it to my model dot encode. So we know that dot encode will give out the embeddings. So I'm going to take that embedding, I'll convert that into a Python list, and I'll return it. Okay, so this function called as embed document will take a string value and it will return an embedding in the form of a Python list. Sorry, this is wrong. Okay, now next step is add documents to ChromaDB with their embeddings. So this will take a whole bunch of documents. It will iterate through each of them, and it is simply going to create the embedding of the document text. So I'm using the embed document function here, and then I'm creating an embedding of it, and then I'm adding that to my collection. Next, I've got one more function called as query ChromaDB, where I'm sending the query along with the top n value. By default it is set to 3. So which means for every query I'm finding top 3 most relevant embeddings, or in this case documents. Same thing. Okay, now query embedding will take my user input, which is query. It will convert that into an embedding, which is this one, and I'm simply doing a query embedding, and I'm passing my top n value. Both of these are being sent to the dot query method. Now the results, uh, I don't want all of my metadata like the IDs and all those things. So I'm just returning out only the documents. So it's a very simple structure here, everything in one place. So these are all of my different documents where I've got a bunch of strings. I'm adding all of them into my collection, and then this is my user input. I'm sending it to query ChromaDB, and then whatever answer I get, those are going to be the most relevant documents. Okay, after getting the results, here you can see it has added all of the documents, and then these are the most relevant results. The culinary traditions vary from region to region, so and so. This is the first one, and Indian food also includes an array of delicious curries. So this is the second one. So these are the two most, or I should say, two top most relevant documents for my user input. Now, this is just giving me all of my this is just taking my user input, and it is going through all of these documents and then finding out which is the most relevant one, and it is giving it out as it is. So I'm getting the entire document. I still have to read the actual document to understand the answer for my question. This is where LLMs will come into the picture. So what we usually do is we will take the query, we will take the relevant documents, we will combine them. After combining, we will add an instruction saying this is the context and this is the question, and answer this question from this context. So let's build that. So here I've got a function where I'm doing the exact same thing. So this function is taking a query and the documents. I'm just combining all of my documents together into context, and I'm building a prompt here. So the prompt is based on the following documents, answer the question. So in flower brackets, I'm just giving the question with an f string, and with this context, it is going to answer this question. Here I'm using OpenAI to get the answer, and I'm returning the answer as it is. So this is a very simple function that we can use to get a proper answer for a particular question. So this is how we can use ChromaDB with an LLM. Now, this is all about ChromaDB. Now let's understand what is LlamaIndex. So ChromaDB, as we know, is a vector database, but LlamaIndex is a vector index. There's a slight difference between both of these. Let's see what the difference is. So in a vector database, it can store vectors, it can give you the most relevant vectors, nothing more than that. If I want to get a proper LLM output, I need to use the LLM separately, I need to pass my query and documents separately, and I'll get a response. Nowhere in this whole block of cell we are using ChromaDB. So that is a disadvantage that you get with any vector databases. So let's eliminate that by using LlamaIndex. Inside of LlamaIndex, here I've written a simple function to load all of the documents from a particular directory. I'm loading them, I'm parsing them, I'm reading everything, and then I am going to send those documents to this function called as createIndex. Here you can see in the very first line we have something called as LLM predictor. So LlamaIndex makes use of GPT 3.5 Turbo by default, so we have to pass the OpenAI API key compulsory. But what it does is it's going to convert everything into embeddings, store them in a vector store, and whenever a user sends a query, whenever we are doing any querying, it will not only retrieve but also it will generate an answer. So this part, whatever we were doing manually with a separate function, will be taken care by LlamaIndex automatically. So if you can see here, I am defining the LLM predictor and I'm passing it to my service context, and then I'm building my index right here, GPT simple vector index. It's a very basic version of vector index. We'll see some other versions as well, but here you can see GPT simple vector index is being created with all of these documents, and I'm giving my service context as well, which will have the LLM that it is going to use to give the predictions. All of this will be stored inside of index, and I'm returning that index. and I've got a simple function here called as query index. So this is just going to take the index and do a dot query, and it will take whatever user input user question is. Based on that question, it will automatically identify the relevant content, it will generate an answer for us, and that answer will be given back to the user. So in this part you can see I'm just loading all of my documents, I'm creating an index, and this is my question. So whatever index I've created, I'll pass it here, and my question will also be passed. So the index dot query will retrieve the relevant content, it will send it to the LLM, it will automatically create a prompt, and that prompt will include the relevant documents and the user input. Both will be sent to the prompt, and the prompt will be sent to the LLM, and the LLM response will be given back to the user directly. So this is an advantage that we get whenever we are using vector index. Here I'm using GPT simple vector index. This is the most basic version of a vector index. Now there are many other types of vector indexes that are available in LlamaIndex. So if I have to show one thing called as tree index, here you can see I'm importing GPT tree index. Everything else is exactly the same. Instead of the simple one, I'm using GPT tree index here. Everything else is exactly the same, no difference anywhere. Okay, so let's go ahead and understand what is the difference between a simple index and a tree index. To understand this, we can head over to this particular page, link will be in the description, and LlamaIndex official documentation explains it very clearly what are the different indexes available and how are they different. So first and foremost, we have uh, summary index where we've got multiple nodes, and all these nodes are linked with each other. So for example, if I have one document, it might have 4 different paragraphs, and after chunking, each paragraph went into one chunk. So 3 of these chunks are related together. So whenever I want to summarize the entire document, I need to make sure that I'm capturing all the information in that document. So all of the chunks will be sent to the LLM. So here you can see when we are doing a query, this is the query, and all the documents will be sent to the response synthesis. So this response synthesis is nothing but an LLM. Okay, so we have used OpenAI here, right? If I scroll up, yeah. So this LLM predictor, this GPT 3.5 turbo, this is the actual LLM. That is this part. Response synthesis is the LLM. It is taking query and all of the nodes. This is for summary. Summary has to contain each and every point. That is why we are sending all of these nodes at once. But when we are doing a particular RAG application where we don't need everything but we want only few nodes, then we will use vector store indexing. Over here, whenever I do a query, the query will be sent and I'll get top similarity. So if the top value is 2, I'll take the top 2 most relevant nodes, I'll take the query, I'll pass all these 3 into my LLM, and I'll get an answer. So this is a very simple vector index, which is what we have seen in the code just now. Now comes tree indexing. So here we have a root node, a parent node, and then the child nodes. So these child nodes are extremely important, but the way we organize these child nodes should be hierarchical. So per suppose if you have 50 or 100 different PDF files or 100 different documents, and they all follow a certain hierarchy, where suppose 20 documents are related to legal, and 15 documents are related to marketing, and 10 documents are related to sales. And suppose sales and marketing both fall under one category and legal falls under a second category. So in that way you can see that all these documents follow a particular hierarchy. Now when you have such kind of a situation, we can use tree index. What this does is, whenever a user sends a query, it will take the root node and it will start checking for the most matching, most relevant child nodes. Here you can see it found the first node from this parent as the most relevant one. Let me zoom in a bit. Yeah, so here you can see it found the first node from first parent as the most relevant one, and the third node from the second parent as the most relevant one, and it is going to send both of these nodes along with the query to the response synthesis. So this is about tree index. Next, we also have keyword table index. It is also doing somewhat of a similar thing, but instead it's based on a keyword search parameter. So multiple keywords will be associated with a particular node, and whenever a user sends a query, I'll extract the keywords, and based on those keywords, whichever nodes are relevant, I'll take them, and along with the user query, I'll send them to my LLM. So these are the different types of indexes that we can use. There's also property graph index, which is a graph index which falls under graph database, which is somewhat outside of the scope of this video, so we are not going to cover that part now. But I hope I was able to explain you some of the fundamentals of vectors, embeddings, vector databases, and also vector indexes. If you have made it this far into the video, then thank you so much for watching. Have a great day. Bye.